Welcome back. We're finishing off the morning session with Gabe Angelini-knoll, who's going to speak on Syntomic cohomology of regular radiance spectra.
All right, thank you so much for inviting me. This has been a really great conference so far. So you will see that many of the same characters will show up in my talk that showed up earlier. So there's a theory that Flintstones and the Jetsons are actually in like the same universe, so it's kind of like that. There was actually an episode where they had a crossover. I don't know if you've seen that one. But yeah, so I guess you can decide whether I'm the Flintstones or the Jetsons. Okay. So this is based on joint work with Cristiano Soni and John Rognes, as well as some joint work with Jeremy Hahn and Dylan Wilson, and then some work in progress with Cristiano Soni, Bob Bruner, Jack Davies, John Rognes, and Tristan Yang, who's here today. So, okay, so first I just want to, so this is a beyond the telescope conjecture, right? So now we know that ln f, the map from ln f to, yeah, well let me say it's not, the map from ln f to ln is not an equivalence when n is greater than or equal to 2. So now we know that. So there's some other questions, though, that this leaves open. So, for example, for which x is ln fx equivalent to ln x? So this is one really broad question that I think is still very interesting. It's actually more interesting now that we know it's not true in general. And then another question that's kind of close to my heart is, so let me just say this. So when is the map from x to ln f of x detecting a lot of information? So one way that it might be detecting a lot of information is if the fiber is actually bounded above. So in this case, x is actually kind of Vn periodic in sufficiently large degrees. So these are two kinds of questions that I will say we can at least answer in some cases as an application of some of these computations. So, so first let me just give an example. Oh yeah, so first let me just say the idea behind proving both of these is going to be to filter our spectrum x. So we're going to filter x and answer the question on some associated graded. Okay. So one of my favorite examples of this is the Lichtenau-Quillen conjecture. So R is going to be a discrete ring, and it's going to be something nice. It's going to be regular. It's going to be have P in it. For all intents and purposes, you should just think of R as the ring of integers in some number field. Then the question, Lichtenau-Quillen conjecture, was about the question of this map. Whether this map is an iso in sufficiently large degrees. So that was the Lichtenau-Quillen conjecture from the 1970s. So it's two separate conjectures, really, each of them. And so this turned out to be resolved roughly in the way that I say here. So it turns out that L1F local K theory satisfies the Tal descent, so we have a kind of slice spectral sequence from the Tal cohomology. So this is by work of Thomason. Algebraic K theory satisfies the Snedish descent. So we have a kind of slice spectral sequence here as well. And then the way this has been resolved is by the norm residue theorem. Voivodsky, also Weibel and Rust played some role. So they proved that this is some aniso in a range, and that determines that this is an isomorphism in sufficiently large degrees. And then one reason why you care about this is that by work of Wiles, you can relate Untitled cohomology groups to special values of zeta functions, and then that allows you to relate algebraic K-theory to special values of zeta functions. Okay. So, so we had as our inputs some regular ring. So I want to say one kind of condition you could put on our ring spectrum to ask a similar question. So R is going to be a connective P1 ring. And then we'll also have a finite spectrum here. And let's just say X is just the spectrum. So first, R is going to be regular. So this is in the sense of Barwick and Lawson. If pi0 of R is left coherent, so this means that every finitely generated ideal is finitely presented. And then pi n of R is finitely presented over pi0 of R. And one of the key conditions is that if you look at h pi0 of R tensor over R h pi0 of R, then this is bounded. So it only has homotopy groups in finitely many degrees. Okay, so that's a notion of regular that we can use. And then we're also going to need to know, so here we had P inverted, so that's kind of like saying that your height 0. So here we want to have some notion of height, and one notion of height, so first we can say R has height, and if Kn star of R is not equal to 0, and K of M star of R is equal to 0 for n greater than n. But it turns out that there's another notion which is nice, and for that I need a subdefinition. So if F is a finite spectrum, so you got F as above, then this has type n. If it's similar to this, but so if Kn star of X of F is not equal to 0, and K of n minus 1 star of F is equal to 0. And then we're going to say that some spectrum has Fp type n if there exists a type n plus 1 spectrum. So I'll call a generic one f of n plus 1, such that f of n plus 1 star of x is finite. So this is some graded abelian group. So what do I mean by it being finite? I mean that it's only non-trivial and finitely many degrees, and then in those degrees it's a finite abelian group. Okay, so here's a big string of definitions. And then, so I want to now talk about refinement of these questions from before. So one of them is just a question I like, which is, I mean, it's a conjecture from Mohold and Rusk. Which is that if, so maybe before I say this, at the very beginning of the talk, I fixed a prime p. So as you, there's always some prime p, and I'm going to p complete everywhere. With the chromatic homotopy theory audience, that's great comment. So, okay. All right. So then, so let's say if x has fp type n, then ln f of x is equivalent to L. So this is a nice class of ring spectra, or of spectra, that such that we might have an answer to this question. So I think this is just a cool question. And then related to the second question, or a higher height analog of this lithium-Coulomb question. So this is due to Osoni and Rognus. They phrase it slightly more restrictively, but so yeah, we're phrasing it with these conditions. So if R is a regular E1 ring with height n and fp type n, then we can ask whether the map, so then the map, oh sorry, I should say is the spectrum and fiber of the map from Ln, the K theory to the n+1 finite localization of K theory bounded above. And I should be honest that I don't necessarily think these are exactly the right conditions for this. I think it's an interesting question to find out also what are exactly the right conditions on R to have a lithium-Coulomb statement. But this is just to rule out some known counterexamples in the non-regular case, for example. So their statement was specifically for suitably finite extensions of the K local sphere. So I'm not going to write on those boards. Are there any questions so far? So I want to make a couple remarks first. So one, so Tristan Yang observes the following. So if f of n+1 tensor x is bounded, then we can determine that the fiber of the map from x to ln f of x is bounded above. So there was an earlier result of Mohold and Rusk, which showed that if you're FP type n, if you're FP type n, then the fiber of the map from x to ln f of x is bounded above. So if you're FP type n, then in particular you're going to be bounded. So Tristan showed that this is sufficient actually, and that's important because there is actually an example. So this is due to Birkeland. This is in the telescope paper. So Birkeland on Levy Schlenk. So there is an example where, so let me just say, so we know that L2F of K of the K2 local sphere, K1 local sphere, is not equivalent to the L2 local K theory of the K1 local sphere. So this is one of the examples of the disproof of the telescope conjecture. And yet, we do know that the map from the K1 local sphere to the L2F K theory of the K1 local sphere, so the fiber is bounded above. So this is exactly the case where we know. So the issue is that the K theory of the K1 local sphere is not FP type 2. So this is why it doesn't contradict the whole Rusk's conjecture, but it does kind of satisfy this one. So I think this is very interesting, but today I'm going to talk about the even nicer case where where both of these statements are going to be true. So I'm going to talk about a family of examples where you have both.
Are any of these fibers bounded below or just above?
They're not going to be bounded below. I mean, so you have stuff, because this is very much not bounded below, and this is connective, but this is very much not bounded below, but then you get stuff from the boundary. Yeah, it's connective.
How would you ever show that a spectrum is not FP type N? Because you have to test it against kind of all possible.
Yeah, so they have a lot of nice criterion for when you're FP type N. So I mean, actually, another definition. So you can be just FP type as well, and then FP type N is a further restriction. And being FP type means that your mod P cohomology is finally presented over the steam-rod algebra, and that's something that you can check. So you can check that it's not represented. And here, so here actually, sorry, there's another thing I can say, which is that, and this property is generic, so you only have to check it for one type N+1 spectrum.
Oh.
And then you can just, so here in this case you can check it, and there is one that's not, where it's not finite. Okay, so let me state some theorems. So I'm going to call this theorem A just for this talk. So it's going to be several different results. So one, this is with Sony and Rognus. And then there's going to be some parts. So first we show that we study this is at p equals 2, and we're considering algebraic K3 of KO. So we answer these questions for KO. So we show that L2F, algebraic K3, is equivalent to L2, K3, and the fiber of the map K of KO to the second finite localization of K of KO is bounded above. So these are two kind of qualitative consequences of some explicit computations. So let me also mention that we actually compute algebraic K3 in this case. I won't give the explicit answer, but we compute the algebraic K3 of KO mod 2 and eta and V1. Okay. And then, so then in work with Hahn and Wilson, we study this in the case of Morava K-theory, so this is at arbitrary heights. And we show that, so this is now all primes and heights. So we show that the Ln plus 1 F localization of K3 of K of n is equivalent to the Ln plus 1 localization of K3 of K of n. And we also answer the second question, so the fiber of the map equivalent to Moncoulin statement. Okay. This is bounded above. And we also compute the algebraic K-theory of K of 1, mod P and V1, extending some previous computations of Sony and Rognus. Maybe I won't write that down. So, okay, so now we're getting into some work in progress. So the methods we use for K of n also work for BP pointing bracket n. So previously, these questions were known in the case of BP pointing bracket n when you equip it with E3 ring structure, the work of Hahn and Wilson. But what we show in our work is that you didn't need the E3 ring structure. You could have done it just if you had E1 ring structure. So let's say, so BP pointing bracket n is going to be any E1 MU algebra form. Then we prove the same kinds of results. Sorry. So we have a telescope result and an electron Coulomb result. And we can also use this to compute the algebraic K-theory of BP pointing bracket 2, mod P V1 and V2. And this extends some, so at primes greater or equal to 5, which extends some previous computations of myself, Osoni, Rognus, Culver, and Honing. I guess I didn't do an alphabetical order, but okay, so this is in progress. And then some other work in progress. So this is the work with Osoni, Brunner, Davies, Rognus, and Yang. So we also answer these questions for TMF. So this is analysis also again at the prime 2.
Can I ask a question? The
Yes.
choice of R in 1, 2, 3, 4 are all regular in the sense of correct and positive, right? So do you have to do this generally for all regular?
So I think that so all of these examples are regular, you're right, that's why we have this definition. I think it probably is possible to prove at least these like more qualitative statements for any regular ring, but it's not, it's not immediate. So. Yeah, maybe also in response to that question, if you assume more structure, so if you have an E3 ring structure, plus some other conditions, then I think that work in progress of Hahn, Rognus, and developer car, also, I think they also recover some of these qualitative results in more generality. But maybe we'll hear more about that on Friday. Okay. So the goal is also to get the K3 computation here, but I can't say that we have that quite yet. Okay. So, okay, so
Sorry, can I ask? I'm not sure if you commented anything about these examples of K-theories, BPNs, and so on.
Yeah.
If they are or are not FP type, is that known?
yes, so in all of these cases, the K-theory of them are going to be FP type. Yeah, so in these it's FP type n+1. Here it's also FP type n+1. Yeah, FP type 2, FP type 3. So we do prove that in each of these cases. Okay. Okay, so we already saw algebraic K-theory, which was a character that showed up in several of the talks before. Now I want to recall some other characters that we like. So I'm hoping that I can pick up kind of where Tina left off and talk a little bit more about some of these different invariants. So R is going to be connective P1 ring, and again I'm going to be P completing everywhere. So we saw that there is a trace map from algebraic K-theory to topological Hushel homology. And there's several ways of thinking about THH. So you could think of it in terms of the cyclic bar construction. You could think of it in terms of this kind of cocenter construction. Or you can think of it as a factorization homology over S1. And then from that perspective, you can see that you have an S1 variable that you can act on. So you have an S1 action. And then you can define the TC minus of R as the homotopy fixed points of that S1 action, and the TP of R as the Tate construction. And one construction of the Tate construction is as the cofiber of a certain norm map from the homotopy orbits to the homotopy fixed points. And so from that perspective, it's pretty clear that there's a canonical map between these two. So we have a canonical map. GC minus of R to TP of R. And so far I haven't talked about cyclotomic structure yet, but we also have cyclotomic structure. So this is some map phi p, which is S1 equivariant. So that allows us to define the following map. So we have TC minus of R. So that's the homotopy fixed points. And we can look at the homotopy fixed points of the map phi p. That's going to land in the Tate construction. And now because we assumed R is connective, we can say by Nicholas Schulze this is equivalent to TP of R. Again, we're also P complete everywhere. And then we can define, so this composite map is I'll just call that phi. So we have these two maps. And we can take the equalizer, and that's TC. So we have a trace map from K3, and so this refines the trace map from K3 to THH. And I want to just say one of my favorite ways of saying that K3 and TC are equivalent. So it's this nice application of the Dundas-Cooley-McCarthy theorem. So more generally, the Dundas-Cooley-McCarthy theorem says that the fiber of this map is nil invariant. But for the purposes of today's talk, we just need the following consequence, which is that if pi 0 of R is either FP or the P complete integers, then there is a fiber sequence, K3 of R, TC of R, suspension minus 1, HCP, 0, and this is a pullback. So in particular, the algebraic K-theory of R is just equivalent to the connective cover of TC of R in this case. So if we can compute TC, then we've essentially computed algebraic K-theory up to this Eilenberg-MacLean spectrum. Okay, so that was my very quick recap of trace methods. Okay. Right. So these were some characters that also showed up in Tina's talk. And next I want to talk about some characters that also showed up in Andy's talk. So So as I said in the beginning, we want to answer these questions by filtering. And the things we want to answer are going to be, do we want to answer some question about the spectra algebraic K-theory of something. And now we've replaced algebraic K-theory with topological cyclic homology. So now we'd like some nice filtration on topological cyclic homology to be able to answer these kinds of questions. Okay, so that's what we want to do. So I want a slightly more general setup than what Andy had. So let's say, let's let A be an E infinity ring, and M a module. And there's also a version of the even filtration, which appears in the appendix of Hahn-Rexed-Wilson, where you do the even filtration over A of M. And it has a similar definition. So you look at maps from A to B of E infinity rings, where this is even, and we apply tau greater to 2 star to M tensor over A with B. So in particular, if M equals A, just a remark, so fill Eve over A of A is sometimes just denoted fill Eve of A. Okay. So this has an associated graded, which is just going to be denoted per Eve. And then I'm going to wave my hands a bit here, but there's lots of variants. That allow us to define motivic filtrations more generally for some functor applied to R. So R is going to be an E1 A algebra, and F is going to range over. So it could be any of these nice trace invariants we have here. So it could be THH. It could be the CP state construction on THH. It could be TC minus. It could be TC, or sorry, it could be T plus, TP, or it could be TC. So there's some motivic filtration. So in particular, if F is THH, then the motivic filtration is just the even filtration. So going back to a question from a previous talk, so note that this allows you to define these filtrations also when you have an E1 algebra, so not just, so if you took THH of an E1 algebra, you lose your ring structures, you just have an E0 algebra structure. But you can still define this motivic filtration, you just have to keep track of the fact that you were working over A. So secretly this depends on A when R is an E1 A algebra. And then when R is an E2 A algebra, then it doesn't depend on A anymore. So that's where Strudowski's work comes in. Okay, so this is a definition, but so yeah, from this definition, we're taking the limit over all maps from A to B, where B is even. It's not so clear how you might compute that. So I want to say a little bit about how you can compute that. So this was hinted at in Andy's talk, but we didn't talk about it explicitly. Okay, so let A to B be a map of infinity rings. I'm just going to write C-alg for infinity rings, so sometimes I might abbreviate this like this. We say A to B is evenly free if for all non-zero even infinity rings even E infinity rank C with a map A to C in C-alge, then if C tensor over A with B is a non-zero wedge or wedge of even suspensions of C. So we say it's evenly free if for any even non-zero even E infinity ring C, when we take this push out, we get a wedge of even non-zero even suspensions of C. So that's the notion of evenly free. And these are these nice covers that allow you to compute the even filtration. So So first, let me just give you a nice little criterion for checking this. So let's let A to be the connective map, or sorry, let me say be a map of connective infinity rings. Then if h pi 0 of A, the h pi 0 of A tensor over A with B is evenly free, then A to B is evenly free. So this is a nice checkable criterion that you can use. Let me just say the idea behind it. The idea is that one way of thinking about being evenly free is kind of being built out of B being built out of A by attaching even infinity cells, and this is kind of checking what's going on with the even infinity cells of B as an A module. So that's kind of the idea. So now let me give some examples. So one is the sphere to mu. So so we have the sphere to mu. One example coming from work of Botmore and Schulze. So if you look at map from THH of R to THH of S. So if R is quasi-syntomic, and we have some nice quasi-syntomic cover. Where S is also going to be quasi-regular semi-perfectoid. Let's not worry about all these definitions, but basically the key thing is that under this condition, you also have a kind of Botstedt periodicity. Then this is going to be evenly free. And so yeah, I'll say why that's important in a second. And then you could look at THH of mu to mu. That turns out to be evenly free. And then some other examples that are important for the KO and TMF examples are, so the map from THH of KO to THH of KU over mu. This is evenly free. and then the map from THH of TMF to THH of TMF 1,3. So this is a form of BP point bracket 2 over mu. So it's an E infinity form of BP point bracket 2. So these are all examples of evenly free maps. And now I should say, so what does this buy you, having this notion? So this allows you to compute the even filtration by descent along some evenly free map. So this is a theorem of Hahn, Raxit, and Wilson, which is that if A to B is evenly free and B is even, then the even filtration is, so I'm going to do it at this level of generality. The even filtration is given by the limit over delta now of tau greater to 2 star of m tensor over A with B tensor over A over plus 1. Okay, so, and this is, again, some kind of, it's like the decollage of the atoms, some kind of Adams-Novikov spectral sequence. So, and then to say, and similarly, for fill mode of F of R, where R is at E1 A algebra, and F is any of these nice trace invariants. Okay. So, so this gives us a nice tool for doing computations. And, right, so something that also showed up in Andy's talk is the corollary of this, which is that the even filtration on the sphere spectrum is the Adams-Novikov, the decollage of the Adams-Novikov spectral sequence. So I will need to use this. So let me recall what's a consequence of this. So a consequence of this is the following. So let's say this as a remark. So if you look at modules, here, let me be consistent with the rest of the people in this talk. So let's say modules over the infiltration of unfiltered spectra. So this, as we saw, this is equivalent to, to what Andy was calling SEN. Alternatively, you could, this is equivalent to cellular C-motivic homotypy theory. So this is related also to work of Jorge, Isaacson, Krause, and Rika. And then there's another formulation due to Strigowski. And then we also understood the cofiber of tau modules. So doing per star here corresponds to taking cofiber of tau modules. And then there's a theorem here as well. So this is work of Fjorge when Zhu. That this is equivalent to the stable derived category of, so I'm going to have some fixed prime and where P completing, so I might as well say BP star, BP, even BP star, BP comodules. Okay, so what is, okay, I wish I had me move this so I have more room.
Can you explain a bit more detail what's that category at the bottom right?
Yeah, so it's like, it's due to Hovey originally. It's like this, you take even BP star, BP comodules, and you invert stable equivalences. There's a kind of, yeah. So this is, yes, this is carrying. Okay, so what's the key takeaway for this talk? What we need is that if you look at BP star mod P through the n, so this is something that is like a Smith-Toda complex that lives in this world. That's going to correspond to Smith-Toda complex over here. So in this kind of Gur-even land, Smith-Toda complexes just exist for all n. You don't have to worry about the existence of Smith-Toda complexes. And moreover, this is a commutative algebra on this side. So, and this is a monoidal equivalence. So actually, this is also an E-infinity ring. So this is an E-infinity ring, or E-infinity algebra, let's say. So that's really useful. And then there's other kinds of examples that will come up. So you could also take some finite complex, such that its BP star homology is concentrated in even degrees. So for example, you could take the sphere mod 2 and eta mod v1, or another name for that is a of 1. So this name is because its cohomology is the subalgebra of the Steenward algebra a of 1. So that corresponds to something I'll call a of 1 here, a of 1 bar. And then you can also do something with a of 2. So there's a spectrum, it's like z mod v2. So BP star at a of 2. And that corresponds to something I'll call E of 2 bar. But in this case, we're not so lucky. So in this case, these are not U1 rings. Not U1 algebras. So yeah, so this is great. This makes things our life a bit more complicated, but you can still use module structure over this, for example, to study these.
Vn bar is E-infinity, or is that what?
Yeah, it is somewhat I mean, you just need to know this equivalence is monoidal, and then you show that this is a commutative algebra in BP star BP comodules. So it's pretty fun.
In the examples that you listed after the Vn bar, when the equivalence is still monoidal and there is no, when you're saying there is no E1.
Yeah, the problem is already here. There's no ring structure on these BP star BP comodules. Yeah.
Sorry, what do you mean by Z?
Oh, sorry. Let me just erase that. There's a spectrum Z where if you know what that is, then it has a V2 self-map, and its cohomology is A of 2. Yeah. So it was constructed by Bhattacharya and Egger. So, yeah. All right, so now I'm ready to state theorem B, from which theorem A follows. so first, so what do we do? I need some more notation. So if X is something in here, and I have one of these finite spectra, so let's say, let's say we have some F bar, so one of these, then I'll write F bar star X, and that's going to mean the homotopy groups of F bar tensor over Gur-Eve star the sphere with X. So it's just homotopy groups in this category of Gur-Eve images, or like homology in the category of Gur-Eve images. Okay, so first what we do is we compute the A1. Oh yeah, so I might also further quotient by V2, further quotient by V3, and then I'll just do the same thing here. So let me just say the simplest version of what we prove. So we compute yes, thanks. So we explicitly compute the Syntomic cohomology with A of 1. We actually compute it with A of 1 bar coefficients as well, but let me just say that mod V2, we compute it and it is finite. So it's a bigraded abelian group, and so I mean it's finite. It's only non-trivial in finally many bi degrees, and in those degrees it's finite. Yeah, so let me just say that for now. So yeah, and also so there's a spectral sequence that goes from this. So if we didn't quotient by V2, there's a spectral sequence that goes from this to the honest TC, and that's how we prove the part C of the first two. And then in work with Hahn and Wilson, in the interest of time, when we combine these, so this is going to be, we compute Vn plus 1 bar star Syntomic cohomology. Yeah, sorry, I think I didn't say this before, but so this Guermot TC is sometimes called Syntomic cohomology. In the case of TP, it's called prismatic cohomology. Okay. All right, so we compute this. And Vn plus 1 bar star. The same thing for BP20 bracket n. And they are finite. And then in this work with, let me just abbreviate the names, so Sony, Brunner, Davies, Wallace, Yang. We also compute. So remember, this was in progress, this was in progress. We compute this. Okay. Oh yeah, sorry, I should say. It's finite. And in this case, I actually have a picture. So this is roughly what it looks like. So it's in these, so it's bi-graded, so that's why it's depicted in this kind of grid. And one thing that's kind of cool about this is you can see that there's a kind of rotational symmetry. So it's exhibiting a kind of duality, a kind of arithmetic duality that is that currently John Rognus, Jeremy Hahn, and Sonnet Developer Car are working out in larger generality. So I think we might hear about that later. Yeah, so this is, in fact, we also compute the A2 bar cohomology. I mean, so the V3 Bach-Stein spectral sequence collapses in this case. It's actually something you can deduce from this picture. So this is actually, gives you the generators of a polynomial V3 module as a polynomial V3 module of this. But we do expect to have differentials in the motivic spectral sequence. So in particular, I think there's a differential on V3 squared, D3 differential on V3 squared here. That's sort of working.
Sorry, what is the range of this picture?
Sorry?
What is the range of this picture? What is the kind
Does it say 40?
Yeah, oh, sorry. So it's from -1 to 37.
Uh-huh. Thanks.
Okay. Let's see if I can see what I can say. I prove these things. Oh yeah. So maybe first, let me just say roughly speaking, the bound in this direction is telling you something about the Littmann-Quillen. So I say Littmann-Quillen result. And then the bound in this direction is, roughly speaking, telling you something about the telescope conjecture. So the fact that it's bounded in both is roughly saying that you have both. So that's the proof of B implies A. Just in this. At least for parts A and B. Okay, and then I don't have a lot of time left, but I want to just briefly sketch like what steps go into this. And I'm going to do this in a kind of broad way so that it applies in each situation, but it's maybe being a bit, I mean, there's a lot of work that goes into this, but let me just say this in broad terms. So first, there's a THH computation, and yeah, so I'm gonna have a little. I'm going to try and do this in every case. So F bar is going to be either you have 1 bar, you have 2 bar, or you have N bar, and then you have N bar. R is going to be either KO, TMF, connected KLN, or BP on bracket N. N is either going to be 1, 2, and N. And then P is either going to be 2, 2, P, P. Okay. So in each of these cases, what you can show is that if you take the F bar homology of THH of R, then what you get is some E, which is some kind of Poincare duality algebra, and then adjoining the class mu. So I want to say mu to the p to the n plus 1. And so this class mu comes from, let me put this on my side, so THH of FP is polynomial on a class in degree 2, which I'll call mu. And then I'm always going to name this class by its image in THH of FP. So the first step is a THH computation, which uses the this explicit evenly free cover. The second step is a kind of Siegel result, Siegel conjecture type result, which is that it's a kind of strong form of the, it's a strong form of the weak Siegel conjecture, I can say. So what do I mean? So this is going to be E and then mu to the p to the n plus 1. And then this is going to be E and then mu to the p to the n plus 1. And then mu n minus p to the n plus 1. And this map is given, this is the phi p map, and it's given by inverting mu to p to the n plus 1. So the classical Siegel conjecture was about this kind of map being an isomorphism after p completion. Here it's an isomorphism in sufficiently large degrees, but it's a bit stronger because it's actually given by inverting a specific class. Okay. And then step 3 is it's something that was kind of first observed in Nicholas and Schulze, and then generalized in the work of Hahn and Wilson. But then there's a kind of useful isomorphism. So in Hahn and Wilson, it's in a very specific case, but it works more generally, so it's going to work in all these cases. So if you look at f bar mod vn plus 1 star Gamote GP of r, that turns out to be isomorphic to f bar star THH of r GCP. That's nice. So basically, from these two steps and then this, we already have computed the prismatic cohomology. But then if we want to get at TC, we have to actually, we want to compute, we want to compute the spectral sequence, this kind of Nygaard filtration. So there's a spectral sequence like so. So we need to compute the spectral sequence because the TC minus sits inside here. And so the way to do that is actually by detecting certain classes. In Gamote TC minus. So roughly in all of these cases, that's how you do this. And then maybe the final step is so the final step is to compute the co-equalizer. So just say that in step 5, we computed Gamote TC minus, and then there's a common phi map. And so we actually want to compute the kernel and co-kernel of this map. Okay, and then I will end there.
Questions for Gabe?
Say a little more about step 4.
Yeah, so I think a lot of these other steps can be kind of formal. I think step 4 is the least formal. So it's a bit different in each case. It's like so I guess the classical statement for K3 of Z is like you want to detect alpha 1 as like this class T times lambda 1, and then you also want to do lift certain classes to K3. So like you want to lift lambda 1 to K3. So in a sense, you know that you're detecting it in TC minus. So yeah, you want to understand the image from something you understand maybe better. So you want to understand, for example, the sphere well enough that you can kind of map certain classes in, and that tells you which classes are going to be permanent cycles in this spectral sequence, which allows you to determine the differentials.
Mapping the fixed versus
yeah.
and using information about the first.
Yeah, exactly. So basically, from step 3, we kind of know what the abutment is supposed to be, but you don't know what the differentials are. And the differentials really determine TC minus because it sits inside there. And so to determine what the differentials are, you need to determine enough permanent cycles in the TC minus one. And yeah.
And is this related to some sort of classical dimension?
I'm not sure. I don't think so, but yeah.
You've got all these Gamotes floating around. If I remember correctly, you said that's not exactly the even filtration, but some variant of it.
Oh, yeah, right. So it's dissociated graded of some variant of the filtration, and so once you have these EFF covers, you can be very explicit. So you just take the like I could give you an example. So for example, Gamote of TC minus of KO or sorry, let me just say film note, is given by the limit over delta of tau greater than 2 star of, so you apply TC minus of KO of KU over MU, tensor, and then you tensor over TC minus of KO, bullet plus 1. So then you have explicit cobar complexes, so it's a bit simpler. More generally, what you do is you still take the limit over maps from A to B, where B is even, and maps to B infinity rings, but you're applying some different functors. So you're applying like the homotopy fixed point to the tape construction, and you take the limit. And you take the limit not in the infinity rings, but in like cyclotomic spectra or spectra with S1 action. So that's also important.
This statement that THH MU to MU is evenly free. That
Yeah.
sounds quite strange to me.
So the idea is that then you should then if you take THH of R. So basically THH of MU. So MU being evenly free means that if you have an so this is closed under base change. So if R is E infinity, then you would also have the THH of R to THH of R over MU is evenly free. So maybe I just say that to say maybe it shouldn't be so surprising. But maybe another thing I can say is, so THH of MU is just, its homotopy groups are MU star, and then you have a bunch of exterior generators. So the exterior generators are going to be, when you take Tor over that, you're going to get something in even degrees, and the MU star part is canceling out with this. Okay. So, yeah.
I think you may have mentioned this at the beginning, but can you remind me how the vertical and horizontal bounds of your chart relates to everything on coin and the telescope?
Yeah, I can say that. So, I mean, the telescope part is a little bit, well, yeah, so let me say the Lichtenbaum-Cullen one. So from Tristan's results, you know that if you have some finite type N spectrum, or type N plus 1 spectrum, such that if you smash that with TC, it's bounded, then you have the Lichtenbaum-Cullen result. So that's what you want to check, is that there exists some finite type N plus 1 spectrum such that tensoring with it is bounded. And there's some spectral sequence from this to the A2 homotopy of Gabriel star of TC TMF. Or maybe I should be more careful. Let's see. So if you take A of 2 mod some high power of V3, then that's also still going to be bounded, and then that's some spectrum that exists, and then so this is some spectral sequence converging to that, and then that was so that tells you that that's also bounded. I think so. The telescope conjecture part is a little bit slightly more subtle, but you should think of like it's kind of like telling you that you're like MU nilpotent if you have a horizontal vanishing line here. That's.
Joe, can we thank our speaker?